The International Space Station stands as one of humanity's greatest engineering feats. It's a massive space laboratory and habitat orbiting the Earth, where astronauts from different nations live and work together in pursuit of scientific discovery. What makes the ISS remarkable is not just the purpose, but how it was built in space. Unlike traditional construction projects that take place on Earth's surface, the ISS was assembled piece by piece in orbit over the course of more than 10 years. It's a story of ingenuity, precision, and teamwork, as countries from around the world come together to build a functioning space station in the most extreme and hostile environment imaginable. The concept of the ISS was born in the late 1980s, when space agencies around the world recognized the need for a permanent human presence in space. NASA, the Russian space agency Roscosmos, the European Space Agency, and the Japanese Aerospace Exploration Agency, and the Canadian Space Agency all saw the potential for a shared platform for scientific research. The idea was that this would not just be an American or Russian station, but a joint effort that brought together the expertise, resources, and capabilities of many nations. The political and scientific motivations behind its creation were multifaceted. On one hand, the Cold War had recently ended, and the collaboration between Russia and the US was a powerful symbol of peace and cooperation. On the other hand, the space station would serve as a cutting-edge lab for conducting research that's impossible on Earth. From studying the effects of microgravity on the body to exploring new materials and tech that could benefit life on Earth, early designs were developed in the 80s with NASA's Freedom program and the Russian Mir-2 project. These initial plans eventually merged to form the ISS as we know today, and the collaboration became a powerful symbol of unity post-Cold War. Building a space station in orbit presented a major challenge. How do you launch and assemble massive modules in space? The answer lay in international cooperation and the development of advanced spacecraft and launch vehicles. The components of the ISS, its solar arrays, living quarters, labs, and external systems were too large and heavy to be sent up in a single mission. Instead, NASA's space shuttles played a key role in transporting the modules to space, as it could carry significant payloads into orbit and rendezvous with the station for assembly. In addition to the space shuttle, Russian Proton rockets and Soyuz missions were used to deliver critical components such as the Russian modules and the life support systems. The scale of the undertaking was staggering. Each module had to be carefully designed to be launched as a compact payload, then expanded or connected in space, often through spacewalks or the use of robotic arms. The modules were carefully constructed to be as light as possible, while still maintaining structural integrity. Additionally, the weight limitations of launch vehicles meant that assembly had to be done in space, with astronauts performing intricate tasks to fit together these enormous pieces. The ISS was not built in a traditional sense. It was assembled through multiple space flights and careful coordination between all the space agencies involved. The first building block of the ISS was the Russian Zarya module. Launched on November 20, 1998, Zarya, which means sunrise in Russian, was the first piece of the puzzle to reach orbit, and its significance can't be overstated. The module was responsible for providing propulsion and electric power to the nascent space station. Zarya's primary role was to act as the initial core of the ISS, helping to maintain the station's orbit and power supply. It marked the beginning of the ISS assembly, with NASA and Roscosmos' joint commitment to creating a functional space station. Zarya was a symbol of international cooperation from the very start, as it was funded primarily by the US but built and launched by Russia. The partnership demonstrated how former Cold War rivals could come together to achieve something greater than the sum of their parts. This was a crucial step in the creation of the ISS, and its successful launch and deployment set the stage for other components that would follow. From this point on, the ISS would be built incrementally, with more modules launched into orbit, each adding to the station's capabilities and bringing it closer to the full operational form. The assembly of the ISS was one of the most complex engineering challenges ever. Unlike traditional construction projects where materials and workers are on the same planet, the ISS had to be pieced together 250 miles above Earth in a hostile, weightless environment. This process involved sending up individual modules, some weighing as much as 20 tons, and then joining them together in space, often with astronauts performing spacewalks. Astronauts played a crucial role in the assembly, operating outside the spacecraft to make precise connections between the modules. Spacewalking involves a lot of physical risk and incredible precision, as the astronauts had to attach various components such as docking ports and more, and astronauts would also use standardized tools such as power tools, screwdrivers, and even mechanical wrenches designed for zero gravity. In addition to manual work, robotic arms like the Canadian-built Canadarm2 were used extensively in the assembly. The robotic arm was used used to position and attach large modules to the station, reducing the physical strain on astronauts. The installation required impeccable timing, as astronauts often only had a few hours to complete each task, and the work had to be done with extreme precision to ensure that the modules were connected safely. The entire process of connecting each module, calibrating its systems, and verifying its operations was not just a matter of muscle, but a test of fine-tuned coordination between astronauts, robots, and ground control. Over the course of the ISS's assembly, several milestones marked the station's transformation from a collection of modules into a fully operational lab. In 2001, the installation of the American Destiny Laboratory module was a significant milestone. Destiny became the primary research lab in the ISS, allowing astronauts to conduct a wide range of scientific experiments. From medical research to physics studies, the module also helped solidify NASA's roles in the ISS and the U.S. commitment to the project. The European Columbus module, launched in 2008, was another significant addition to the ISS. Columbus provided the European Space Agency with its own scientific research lab, expanding the ISS's capacity to conduct experiments in microgravity and offering a base for European astronauts. Shortly after, in 2008, the Japanese Kaibo lab was added, further expanding the ISS's ability to conduct specialized research, particularly in life sciences. Kaibo, with its unique external platform, allowed for experiments in the vacuum of space, increasing the station's ability to carry out long-term biological research. As these modules were added, the ISS began to take shape as a fully functional space station, equipped with the support for long-term duration human habitation and scientific exploration. Astronauts not only worked on the assembly, but also adapted to the challenges of living in space during this period. They followed rigorous work schedules, conducted scientific experiments, repaired equipment, and even participated in outreach, such as communicating with students and the public. Each new addition brought the ISS closer to its full potential, making it the most advanced research facility ever constructed. The construction of the ISS was not without its significant challenges, both technical and logistical. One of the biggest hurdles was coordinating the complex timing of launches, deliveries, and spacewalks. The Space Shuttle program, which was essential to transporting modules to the station, had its own challenges, including delays and occasional technical issues. The consistent need for communication between astronauts in space, mission control on Earth, and the spacecrafts in transit added another layer of complexity. Spacewalking posed significant risk to astronauts, as every EVA came with the dangers of equipment malfunction, space debris, and even harsh environmental conditions of space. Astronauts faced extreme temp, limited visibility, and the physical exertion of working in bulky spacesuits. Additionally, the lack of gravity made routine tasks complicated, requiring specialized tools and techniques for even simple actions. Beyond the immediate risks of spacewalking, the station's construction was affected by unforeseen delays and equipment malfunctions. For example, some modules were delayed due to manufacturing issues, and there were problems with the Russian-Progress spacecraft that affected the station's supply chain. Hardware failures and repairs in orbit also became routine parts of station life, as astronauts worked to fix systems like the cooling pumps, life support systems, and solar arrays, which sometimes required improvisation and creative solutions. Robotics and automation played a pivotal role in the assembly and ongoing maintenance of the ISS. The Canadarm2, a robotic arm designed and built by the Canadian Space Agency, was critical for station assembly, used to position modules and perform repairs without the need for astronauts to perform spacewalks. Canadarm2 was capable of operating with high precision, allowing it to lift heavy loads and move components with great accuracy. This technology was essential for reducing the risks astronauts faced while increasing efficiency. In addition to Canadarm2, another robotic system, such as the European Robotic Arm and the Japanese Kaibo robotic systems, contributed to the assembly and operation of the ISS. The integration of robotic arms in the ISS made it possible to carry out delicate tasks with minimal risk and with fewer astronauts needed. Automation also played a key role in station maintenance. Over time, advanced robotic systems became essential for tasks such as monitoring equipment, conducting repairs, and ensuring that scientific experiments continued to run smoothly. Automated systems not only allowed for routine maintenance to be conducted more efficiently, but also increased the reliability of the space station systems, ensuring that astronauts could focus on their primary research tasks. As robotic tech advanced, it made future space missions more feasible and efficient. For instance, future missions to the Moon and Mars will rely heavily on automation to maintain habitats and carry out exploration tasks, inspired by the success of robotic technologies used by the ISS. If you enjoyed this video and are fascinated by the ISS and space exploration, be sure to hit the like button, share the video with your friends, and subscribe to our channel for more exciting content. We'd love to hear your thoughts on the ISS and any questions you may have about space exploration.